What challenges does quantum coherence create for magnetometry? Imagine trying to listen to a whisper in a noisy room. That's similar to what quantum magnetometers face when trying to detect tiny magnetic fields while keeping their quantum states stable. Quantum coherence is what makes these sensors so sensitive. It's the ability of quantum states to stay in a fixed-phase relationship over time, which is essential for measuring faint magnetic signals with high precision. But this very feature also introduces some tricky problems. First, quantum coherence is very fragile. In quantum magnetometry, like with nitrogen vacancy centers in diamond, the length of time the quantum state remains coherent, called coherence time, limits how long the sensor can detect magnetic fields accurately. Environmental noise, temperature changes, and interactions between quantum particles can all cause the coherence to break down. For example, increasing the number of nitrogen vacancy centers in a diamond can boost the signal, but it also makes the system more prone to spin-spin interactions, which speed up decoherence. So, trying to make the sensor more powerful can actually make it less stable. Second, maintaining coherence is affected by noise that comes from outside and inside the system. External magnetic noise from nearby electronic devices or natural sources can drown out the tiny signals the sensor is trying to pick up. Inside the system, spin relaxation processes can also cause loss of coherence. Even advanced quantum states like entangled or squeezed states, which can theoretically beat classical measurement limits, are vulnerable to this noise. Techniques such as using entangled pairs or special quantum states can help resist noise, but they are still sensitive to fluctuations over time and requiring very precise control. Third, keeping coherence at practical temperatures and conditions is tough. Quantum coherence times tend to decrease as temperature rises. For nitrogen vacancy centers in diamond, operating above 1000 Kelvin causes rapid spin relaxation, making it hard to use these sensors in hot environments. Achieving fast heating and cooling cycles to preserve coherence demands complex setups, which limits where and how these sensors can be used. Fourth, scaling up quantum systems while keeping coherence intact is a complex task. Methods like quantum error correction and feedback control can help detect and fix errors during measurement, but they add layers of complexity. Fabricating high-quality diamond chips or other quantum materials that maintain coherence during manufacturing is also challenging. Defects introduced during production can shorten coherence times and reduce sensor performance. All these challenges mean that although quantum magnetometers can detect magnetic fields with incredible sensitivity and resolution, their effectiveness depends heavily on balancing coherence preservation with sensor size, environmental shielding, and operational conditions. Overcoming these issues is key to making quantum magnetometry practical for real-world uses in medicine, geophysics, and materials science, where detecting extremely weak magnetic signals is often essential.